So okay, so in today's session, I'll just answer the questions that have been answered before now. You guys can hear me, right?
Yeah.
Good. So this is the box and the whisker plots that somebody asked in the group. Okay. So first thing first, you see the you need to get a definition of terms. We need to get a definition of terms. So what we call the lowest part here? What do we call it? The lowest part. Can someone answer? Hello? Hello?
Yeah,
we can hear you.
Yeah, we can hear you.
So what do we call the lowest part of the whisker plots? This point here, the lowest. What do we call it? We call it the minimum. So that's the minimum. Okay. So whenever you see a whisker plot, the first thing you need to do is to identify the lowest part, then identify the highest parts. Okay. So this lowest part here is called the minimum. All right. So if they ask you what is the minimum score for group A, what will your answer be?
17.
17.
Good, good. And the minimum score for group B is what?
18.
All right, good. Now, why the maximum score for group A is what?
26.
26.
Why group B, the maximum is what?
29.
29. Now, sometimes you might have some outlier. An outlier is represented by a dot, just like 3 dots, 1, 2, 3. So outlier means like the value is abnormally high. Okay, so assuming you see extra dots like 1, 2, 3, and they ask you what is the maximum. When they say what is the maximum, including the outlier, then the outlier will be the maximum. That means like those people that get extremely high score. Maybe everybody was getting an average of 26, and then somebody comes and gets 90 over 100. You see that? So that's an outlier, right? So outlier is like abnormally high score. Okay, so it can be on the high side, or it can be on the low side. You can have like 1, 3, 2 dots here. You can have like 2 dots. 1, 2, 3. Just to say that, okay, those are the extremes. Okay, is that okay?
Yes.
Yeah.
So now we have identified that. Hello? Hello?
We can hear you.
Okay, let me just continue. Anytime you can't hear me, you speak up, okay?
All
so
right.
the next thing you need to identify is the interquartile. You need to identify the quarter 2. Sorry, you need to identify the quarter 2, the first quartile, and the third quartile. So we have the first, this first line, this line here, the bottom of the box is the Q1. Okay, first quartile. Now this second line is the second quartile, and this one is the third quartile. Okay, and then this is the fourth quartile. So now the quarter 1, Q1 divides the data set. It divides the data set from the lowest 25%. It's the Q1 divides the data set between the lowest 25% and then the rest of the data. So it is important that you note that you are seeing that this one is long here, and then here is short. It doesn't mean that the number of data inside this small place now is smaller than the number of data inside here. No. So what it means is that if you put all the data sets in a straight line, okay, if you put all the data sets in a straight line, and then you divide that data set into 4 places, into 4 places. So let's say that between here and here, let's say that there are, let's say that you have 100 data points in between them. So if you arrange them in a straight line, 20 in that 100, 25 will be inside here. Now, 25 will also be inside here. Very, very important. What I'm saying is very important. If you bring 100 data points between the minimum and the maximum, if you arrange the data points in a straight line between the minimum point and the maximum point, the number of the number of the data points you will have in this below Q1, that means below from here to the beginning, it will be 25, telling you 25%. The number of data points you will have even in this small place will be what? 25 or 25%. Now, the number of data sets you also have in this space here is also 25. Okay, Sandra, okay, admitted. All right. Then the number of data sets you will see, you will have between here and here is also 25. Okay, so that 25, I mean like 25%. So it's not about the size of this each the distance between the points. It doesn't affect the number of the data set. Okay, so all these things you are seeing that here is wide, here is short, here is wide. They are all telling you about what? The concentration. So let's say here now you see that you have 25% of the data set is between the minimum and the Q1, but they are all spread apart. Are you seeing that? They are all spread apart. Now here, 25% of the data set is also between the Q1. This line here is the Q1. That's quarter one. The first quartile, and then this is the second quartile, or you call it the mean. So 25% of the data set is also inside this small space. So here the data set is more concentrated. Are you getting that? Are you seeing that? But it's the same number of data sets. So here is 25, and here is 25, here is 25, here is 25. Okay, but then what these shapes are showing us is what? The concentration, how the variability in the data set. So between Q1 and the minimum data here, you can see that here there is more variability. Okay, it's less concentrated, right? But you see here between Q1 and the mean, which is Q2, the data is more concentrated. Are you seeing that? Now, between Q2, which is the mean, and Q3, you can see that the data is less concentrated. So that means there is high variability in the data set. Is that okay? Now, between Q3, which is this one, and the Q4, which is the maximum, there is also a little bit of what? Variability. Is that okay? So in the exam, you'll be asked, basically, it's not too much, you don't need to derive any formula, but you'll be presented with something like this to interpret and maybe compare the two groups. Okay, so now what is the mean for group A? Based on what I've said now, what is the mean for group A?
That's 21.
Yeah, 21.
21. And what's the mean for group B?
23.5.
Okay, 23.5. Okay. So like I said before, I'm trying to define the concept. So Q1 means that what? The first quartile divides the data sets. Okay, it divides it between the lowest 25% of that data and then the rest of the data. That is what for Q1. Okay, now Q2, the mean, sorry, not the mean, sorry, this is median. Sorry, this is median. So the median divides the lower 50% of the data and the upper 50% of the data. So now from here to here is how many percent based on what I taught you now? From here to up to the maximum, how many percent do you think it will be?
50%.
50% is very, very important to, you will not say that because the hair is small. So each section is 25%. Each section is 25%. So have it in your mind. Each section is 25%. So now, how will you calculate the range of the data for group A? The range is what? The maximum
Highest minus
minimum. So that would be what?
26 minus 17.
17. And 26 minus 17 will give us what? 26 minus 17. 17 plus 3 is 20. 9. So that's 9. Good. Now, what's the range for this one? For group
29.
11.
That's 11. All right. So now, if I asked to write a report on this, let's say that these are these are the dancers' ages now. So how will you write it put it in writing? First sentence based on range.
So group A.
Yeah.
Has a range of 9.
Okay.
Has a lower range compared to group B.
Group B, correct. So okay, so group A has a lower range, or group B has a higher range compared to group B. So what else can you write in the report? You have written about the range. What else are you going to write again?
Those in group B are older than those in group A.
How will you put it in writing? So now remember, listen to me. How many percentage is from the beginning of this box to the end? How many percentage is it?
50%.
So good. So now, how will you compare this box to this box?
Okay.
So here I will say what? That on the remember that this box here is generally higher, okay, than this one. Okay. So I can say that on the average, I can say that if you're looking at the median now, you can say that the median age for group B, okay, falls around 23.5, okay, then compared to the median age of group A, which is what? 21. Good. Yeah. So now there will be another scenario where this box is very, very small. So assuming that this group B is very, very small, what are you going to say? So assuming that I block out from here to here and just you have only this small box, how will you describe that when the box is very, very small? When the 50% is very, very, very small, how will you describe that? So you will say that there is what? Less variability. So you will say that 50%, okay, 50% of the middle 50% of the data set, okay, is concentrated around the median. So, but that scenario is not here. So I can see here that there is a large variability in the middle 50% of the data, both for group A and group B. So I described from here to here as what? The middle 50%. That's how I described it. From here to here, or from here to here, that's the middle 50%. Now, from between here and here is the upper 25%, okay? While here to here is what? The lower 25%. So that's how you can put it in English language when you're assuming you're writing, depending on whatever depending on the kind of question. So assuming that the whole body of this group B was above this one, I would have said that the middle 50% of B, the middle 50% of B is generally higher than the immediate 50% of A. So that's assuming. Okay. So
Yeah.
how do you calculate your interquartile range? Interquartile range is what? Q3
Q3 minus Q1.
minus Q1. Okay. So that's the much they can tell you. Okay. So like this is just to explain what I was saying before. So have it in the mind that the data is put, if the data is put in a straight line, 25% will be in the first compartment, which is Q1, and between minimum and Q1. The next 25% will be between the median and Q1. It doesn't matter how large it is, okay? Right? Then the next 25% is between the Q3 and the median, and then the last 25% is between the maximum and
Q3.
the Q3. So that's it. I think that settles any question. Good. So I want us to attempt this one. So question number 1, what is the median age? What is the median age?
52.5.
52.5.
2.5, okay, approximately. Okay, now there are more presidents between ages of 53 to 60 than 49 to 2 of us.
False.
False.
No.
Why?
Because there are more presidents between.
No, it's false because they both
The
have
box is
equal.
smaller.
Yeah. So each section of the box have equal number of data points.
Yeah,
exactly.
So it's not about the size of the box or the length, but the content, the data set remains constant. Now, what's the difference between range and interquartile range?
Okay, 70 minus.
What's the difference
35.
between?
And then 60 minus
So
50.
first of all, you tell me the range, then you tell me the interquartile range, then you minus the 2.
Okay, the range should be 71
1 minus
minus 36.
yeah.
30 something.
71, okay, correct. That's the range.
Interquartile range will be 60
15
minus
15.
40. You know the 50.
Okay, sorry.
40 something.
Yeah.
It may be approximately.
Okay, all right, okay. So just at least once you know the definition, you are good to go. All right, now, what percentage of vice presidents were at least 60 years old?
Oh boy. Percentage
At least 60
vice
years old.
presidents.
Okay,
60
so
years. Let me see.
Let me know who will get this one now.
75%.
25%.
It will be like
Correct.
60 or
75.
what?
75.
It's
How many?
25.
I said, sorry, excuse me. What percentage of vice presidents were at least, that's the key word, 60 years old?
Yeah.
So let me see. If you tell me you defend it, it's not about telling me the answer. It's about defending.
The person that got the answer, how did you get it, please?
Okay.
No, he has not got. I don't know.
You've not
I
gotten it,
didn't say that. You
Oh,
can't
they have
answer.
not gotten
It's a
the answer.
mistake. It's just for you to
I
defend.
think it's 75.
I
If you
think
say it's
it's
75,
60 over 75 times
wait,
100.
listen. To
At least 60
what
years.
percentage of the vice presidents see the keyword at least?
I know the answer is 25%.
It's 25% now.
Why? I thought
Because
you said 75%.
At
now.
at least 60 years means 60 and above.
Exactly.
So how did
yeah,
you come about
yeah.
25 now? I thought
25.
75.
It's the
60
last
above, yeah.
This is last,
from the graph there.
Yeah. So you can see
from
only
this
25%.
the
They
third
all have
interquartile
equal
is the
distribution.
last one. Yeah.
Good. Okay.
Sorry, I didn't get that.
Okay. Sorry. Can you explain again? The person that was
Explain again, please.
Okay,
so
from the
Right.
the last interquartile range to the end of the maximum, that's 25%.
Yeah.
Oh.
Yeah.
So assuming you arrange the data sets in a straight line and divide it into 4.
Yeah.
If you divide it into 4, they will be all equally distributed. It's not about
Exactly.
the size. It's not about the size of the box,
Okay.
right?
Mm.
That's just it. So they have equal number of data sets. All right. Now, can you determine if any president took office at the age of 55?
Determine if any president office after 55. Well. Yes.
You can.
Defend it. It's not about telling me yes. How?
Yes, you can, because we can see that in the third quarter. So see in the third quarter between the Q2 and Q3.
Yeah.
So the presidents will fall. The age 55 will fall under that.
All right. So now the answer is no. The answer is no. Okay. Interquartile range. It doesn't look into the data sample.
Okay.
It's only looking at the variance, the variability. So anything about whisker plot, it doesn't identify the data sets. As you can see, they have equal distribution in the data set. So it doesn't look into it to know what's happening. It's only concerned with the variability, the variance, how concentrated the data is. Okay. So
sorry, I didn't really get that, please.
so I said the box and whisker plot, it doesn't look into the data, the sample itself to find out what's going on.
Okay.
It's only concerned with what's the variability, the variance, how concentrated or how varied, how spread are the data sets. Okay, so that is the purpose of some whisker. It's not to come and start identifying who did, or maybe the number of people that are between this age group. That's not the purpose of box and whisker plot. So what percent were between 49 and 60 when they took office?
50%. 50.
How? Defend it. How do
Between that first quarter
and the last
and last quarter.
25 plus 25.
Yeah.
That's 50.
Yeah.
Correct. Now, true or false? Half of the vice presidents were between the ages of 36 to 49 and 60 to 70.
True.
How? You read the question very well. Half of the presidents, that means 50%, are between the ages of 36 to 49 and 60 to 70. Is that correct?
False. I don't think
False.
so.
See, remember, this 70, this is not 70, this is not 70, right?
Okay, yeah, it's
Remember,
true.
here is 25, here is 25, but 70 is here. So it
yeah,
didn't reach,
it's true.
it didn't reach 50%. Okay. All right. So having said that, so these are now example of box and whisker plots. Now the question is what? How will you describe this data set now?
Question.
Yeah.
The first true or false question is what was the answer again?
What?
The first true or false question.
Okay. More presidents are between the ages of 53. You guys should answer it now. More presidents were between the ages of 53 to 60 than 49 to 53. True or false?
The answer was false.
It was false because they all have 25 years.
Yeah.
So that's this thing. Now the next question. Which city had the lowest mean relative humidity? So can you see here now that the ranges are very, very short, right?
Yeah.
As you have to describe this data, the ranges are the range for this Kahul is the humidity is the data is very concentrated.
Yeah.
compared to Los Angeles.
Los
Right?
Angeles. Yeah.
Okay.
Yeah.
Then if you look at, like I said here, 25% is here.
Yeah.
Yeah.
The medians are fairly the same. They are fairly similar, but then 50% of the data are more concentrated. They are more concentrated with around the median for group. That's for this Kahulu. So 50%, the middle 50% of the data, of the humidity data for this country, they are very, very concentrated. The variability is very, very low. Okay. And that means that you can easily predict the next. That doesn't mean that you are trying to predict what the humidity will be like. It's easily predictable. For this one here, you can see the wideness here. So there is high variability. So it is less concentrated, is less predictable, right? Then you can see that 25%, can you see that this from here is entirely below this one?
Yeah.
So that means that the lowest 25% of the humidity of the mean relative humidity in Los Angeles, they are lower than that of all the data points in this Kahuli country. So the lowest 25% of the humidity of mean relative humidity is lower than that of this country, this Kahulu country. So, and then can you see these two things here?
Yeah.
What do you call them? They are outliers. So if they ask you what is the maximum, if they didn't specify anything now, and they say what is the maximum humidity, it has this one, right?
Yes.
But then if they say what is the maximum excluding outliers,
okay,
you're going to choose this one. All right.
Yeah.
So I think that's basically if you use this data to predict the mean relative humidity from October 1st, which prediction would you be more confident? Oh yeah, you guys should answer this one. B.
Kalui.
Yes, because it is more concentrated around the median. Okay, so you can easily predict this one. Okay, which city had the lowest mean relative humidity?
Los Angeles.
Yeah, that is what this one here, right?
Yeah.
Okay, so we are done with this. So somebody was asking a question about fixed effect and random effect.
Yes.
I don't know whether we are finished watching that video. Just screenshot. You can just screenshot.
Yeah, there is an interference.
Yeah, go ahead. Please, can you mute your mic? I don't know whose mic is making noise. Just one person should ask the question.
I asked the question from the chat. Why I am is noisy.
So what would be the number of outliers? What do you mean by number? Is not indicated now? See, the graph didn't show it. So, but assuming that they won't ask it, they will also include the percent here. You understand? Yeah. It's just for you to know how to interpret. That is just the whole essence. You may not see this one in the exam, but just for you to know how to interpret it. Okay. All right. So now we have fixed effects and random effects. When do you use it? Whenever you hear about these two things, you are talking about meta-analysis. Okay. Please, can you mute your mic? Let me talk. Can you mute your mic? Mute your mic. Let me talk, please. Okay. So fixed effects and random effects. When do you use them? You use them when you are doing meta-analysis. When you are trying to combine data. So somebody that was asking me, what do you mean by effect? An example of effect is mean. Can you see that you have several data sets here of relative humidity, and then you combined all of them, and then you got the mean. Okay, so mean is an example of effect. Okay, odds ratio is an example of effect. Relative risk is also an example of effect. Is that okay? For the person that was asking me about what do you mean by effects?
Yes, yes.
So effect is what, when you combine things together. What one value that you can use to represent other things. Can you see here now? You are trying to use one value to represent all the data. So mean, basically the effects that you need to know is just measure basically mean, odds ratio, and relative risk. Basically, at least for this level. Okay, mean, odds ratio, relative risk. Sometimes the mean difference. If you are comparing two groups, you are comparing average average of the score in class A with average of score in class B. Okay, so that means you are saying that there is no difference. Your null hypothesis is that there is no difference between the mean. So mean difference is also an example of a measure of effect. So whenever you are reading an article, when you come across all those terms, mean difference, mean, odds ratio, relative risk, those are effect sizes. Okay. All right. So
Sorry, sir, what about this standard deviation?
they are all, as like, you cannot just say mean alone now. Okay. So you have to state the range within that mean. Like, as like you are saying that let's say if the mean is 30, let's say if the mean here is, okay, let me get notepads. So in research, you don't just mention only one figure and you stop there now. Okay, so you have to state the interval where that figure is valid. So if you say the mean is 30, what is the range? What is the boundaries? So let's say 30 plus minus 5. Okay, so 30 plus minus 5 will be what? It will mean that the range is what? From 25 to what?
Sorry, I'm not understanding.
What don't you understand, I beg?
The one you're explaining now.
No, somebody was asking me about the standard deviation. Is that not what you're asking, Abby?
Yes.
So I was saying that whenever you mention mean, you ought to state the standard deviation of around that mean, because in real life you cannot, even if you do, for example, you do a research today and you get the mean as 30. Then another researcher does the research and get the mean as 32. Another person does the research and get the mean as 28. Okay. Now that person does the research and get the mean as 25. That person does the research and get the mean as 33. Now and then 100 persons. That's this research is repeated 100 times, and all the values fall within 25 to 35. So I'm just trying to explain what that standard deviation you're asking me is.
Okay.
So sorry. So standard deviation is what? The deviations from the mean. So if you add all these things together now and get the average, if you add these numbers together and get the average, okay, then using the formula of standard deviation, I don't want to go into mathematics because you are not expected to start cramming all those formulas. So that standard deviation it explains the spread of the data, the variance of the data sets from the average, how the data set varies from the average figure. Okay, that is for standard deviation. So standard deviation, we are talking about assuming that all the data sets are ranging between 25 to 35. Okay, and then using some formulas, the formula for standard deviation, you can, if you have the sample size and then you have the total number of data sets, you can calculate a standard deviation. Okay, and normally, let's say the mean is the mean of a set is like 30 plus minus, let's say plus minus 5. That's plus minus 5 is the standard deviation. So if you repeat if another person does that research, the mean will always fall within that range of that standard deviation. So that it means that all these things here now are still correct. So that somebody did and got a mean of 30, another person did and got a mean of 32 in different countries. They are all correct so far as they are within that standard deviation. Is that okay?
Yeah. Okay.
So that's for that is for mean. Now another concept is when you talk about confidence interval. Confidence interval. So let's not. We'll do that one later. Let me finish my presentation. Okay. So I was talking about fixed effects and random effects. So if you are, from the last video we did, we talked about heterogeneity. Heterogeneity is when you are trying to combine studies that are entirely different. So let me show you an example of studies that are entirely different. Can you see? These are 3 studies. This one was done among the elderly. This one was done among people aged 21 to 40. This one was done among adolescents. So can you see that the study is heterogeneous, right?
Yeah.
They have different means. So the mean age for this one is different from the mean age of this one. It's different from the mean age of this one. Okay. So that means these studies, you are trying to when you're combining, when you do your calculation and you determine that this meta-analysis that you are doing, that these studies are heterogeneous, then you have to use the random effect. Okay, the random effect. So look at these means now, they are very, very far from each other. Are you seeing that? This one is 1.1, this one is 7. So the variance is too much. Okay, so and then the age group are also different. So in random effect, when you use it is when you have done your calculation. That's when you're doing meta-analysis and you see that the studies are heterogeneous. That means they are significantly different from each other. So that is for random effects. Okay. Now fixed effects. Can you see how close the mean are? This is fixed effect. For fixed effects, can you see that these studies, they are almost similar, right? So instead of doing a simple average, remember this is the mean score for this study done in St. Louis. Yeah, this one is the mean score for the one done in Chicago. This one is the mean score for the one done in Seattle. Now this one was the sample size was 1,000. The sample size for this one was 100, and the sample size for this one was 200. Now, how do you combine? Assuming you're doing meta-analysis, how do you combine the mean data? It's not just ordinary 4.8 plus 3.9 plus 5.3 divided by 3. No, because you didn't include the
Sample size.
The sample size. So what do? You multiply the mean sample size for each of them, okay, and then divide by the total population. Do you understand? So that's what you know when you get your pooled mean. Remember, we have pooled odds ratio, pooled risk ratio, and then the pooled mean score. So those are the effect sizes for meta-analysis. When you are doing meta-analysis, so you are not expected to know how to do it, but the most important thing is for you to know how to interpret. Okay, so like I said, so fixed effect model is when the studies are homogeneous, right? So if you watch the videos, what is the statistic that we look at when we're trying to interpret meta-analysis to know whether it is heterogeneous or homogeneous? What is the test that we look at? Let me see.
Chi-square test.
Test of heterogeneity.
Good. Chi-square test of heterogeneity.
Yeah,
So
heterogeneity.
what do we say is the value when it is? Can someone tell me about the value because it has been long. Can someone remind me? So how do you interpret it? Check your jota if you have jotted it down.
When p-value is less than 0.05
Okay,
or
that's
greater
the
than
p-value of
0.05.
the chi-square, right?
Yes.
The chi-square. Good. So when the p-value is less than 0.05, what does it mean?
It's significant.
It's significant.
Yeah.
Good.
Yeah.
Now, what does it mean to have a significant chi-square test of heterogeneity? How will you interpret it? When it is significant, what does it now mean? Does it mean that the studies are heterogeneous or the studies are not heterogeneous? Which one?
It means
That
they're
is-
they are homogeneous.
Okay, it means that they are homogeneous, right?
Yes.
Is that correct? Other people, can you confirm from your jota?
Wait, let me
No, wait.
confirm from my jota.
Sorry, what's the question? What's the question
In
again?
other words, they are less heterogeneous.
The question is, how do you interpret chi-square test of heterogeneity in meta-analysis?
Yes, according to the lecture, it said that we will want our study to have a low heterogeneity.
Yes.
That means it should be more homogeneous.
Good. Good.
So,
So,
in other words, if it's less than 0.05, it's homogeneous.
okay. Okay. So I want us to get that. So when the chi-square test of heterogeneity is less than 5%, that means that the studies are homogeneous. So that means that the studies are similar to each other, right? So now, which model are you going to now use which model do you prefer? As someone that's based on the knowledge I've told you now, are you going to use a fixed effect or are you going to use a random effect?
You're going to use a fixed effect.
Yes, so you can see
Fixed
that.
effect.
Yeah, so now I'm not going into detail on how to calculate the fixed effects. It's not important. All you need is to learn, go and download meta-analysis on any topic at all. Read the
Wait,
article. Yeah.
I have a question. Wait, are you saying
Yes.
if p-value is less than 0.05,
Yes.
the studies included are heterogeneous?
No, they are homogeneous.
They are homogeneous.
They are similar. They are similar. Similar setting.
So they are significant.
It is not about significance. Yeah, when the p-value is significant, which is less than, yes, when the p-value is significant, that means that it is less than 5%, right?
Yes.
Yeah.
Then that means that the studies are homogeneous.
Yes.
Okay.
For the chi-square test of heterogeneity. Okay, so what you need to do now is to download any meta-analysis. Go to Google, meta-analysis in any topic at all. Try and read it. Check all the things that we're saying now. So you will see how did they interpret it. So that's your own work now to do. By the time you read 2 or 3 meta-analysis, that will now help you. You will now understand what they are talking about. Okay, so you use computers to do all the calculations. There is no need in trying to derive formula. There's no value in all those things because computer can do all those things. All right. So okay, so I think I've explained all these ones. So random effect model is what is used for what? Heterogeneous. When the studies are heterogeneous. So the studies are weighted both by the size of the population and the distance between other studies. So what do we call this? What do we call this? What do we call this? Where do you see something like this?
Is it that forest plot?
Yes. Good. So yeah, who can interpret this one for me? Who can interpret, at least, even though you may not get the accurate distance, but then it's okay.
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 It has to do with it crossing the line. So
which line? Is it line of 0? Well, now listen, it depends. It depends.
Okay. Yes.
If you are looking at odds ratio and risk ratio, remember that when the odds ratio and this ratio, when they are 1, it means there is no
association.
So it means that when this line touches this one now, any study, these are different studies now. Can you see that this one, it's crossed line, it's touched the line of 1. So that means that there is no association here for this one. This one touched it 2. This one touched it 2. This one touched it. So these 4 studies now, there is no association between A and B, between the outcome, the outcome and the independent
Exposure.
Okay. So, but you see this one, it didn't touch it, and we say that when it is less than 1, it is what? Protective, right? It's protective.
Yeah.
Assuming it's a vaccination. So this one is protective. Which other one again? This one, and then this one. Then there is normally there is that big one. They pulled odds ratio. Now look at this one. Let me see who will get this one. What is the effect size for this study? Remember, I told you that there is different effect sizes. I'm gonna give you examples. Now, let me see who will get this one. What is the effect sizes for this one?
Okay.
For which one?
What study is this, first of all?
Yeah.
What
What
study
type of
is
study?
this? Is it a case control?
Okay.
Okay,
I don't have that data here. It's okay. I don't have that data here. Okay. Yeah. It's okay. But at least the most important thing is for you to know how to interpret it. Okay. So for odds ratio and relative risk, when it touches 1, or when the confidence interval crosses 1, it means what? It is not significant. Okay.
Yeah.
Where is confidence interval?
That
Where is the
here,
confidence?
this is the confidence interval. See. Okay, no. Okay.
Oh my God.
It's not shown here. It's not shown here. But normally,
Okay.
they will write the range. Okay. So this one is still dealing with fixed and random effects, but I'm trying to use it to explain the Fourier plot. So it's not in this one. Okay. So, but if you go back to that video, it's simple. For odds ratio and relative risk, anything that concerns 1 makes it what? Insignificant, assuming that is the Fourier plot. Okay. All right. So.
Sorry, I have a question.
Yeah,
when it touches line 1 or crosses it, that means there is what? Or there's no association?
There is no association. Yes.
Okay.
Yes. There is no association. Okay.
Okay.
When it touches 1, that is for odds ratio, and that's for ratios generally.
Yeah.
Remember that you cannot have a ratio of 0, right? Can you have a ratio of 0? No. Can you have a ratio of 0 in your notes? Ratio is
no.
So you can only have 0 when you are comparing the difference between 2 means, right?
Okay.
So mean weights in group A, mean weights in group B. So when you're comparing the difference, so that you can see that okay, A, the average weight is more than the weight of group B. So whenever you have mean or mean difference, then that 0 becomes important, because mean difference is not a ratio. So when that line touches 0, or when the confidence interval crosses 0, then that makes it what? Insignificant. Okay, as for mean difference. So ask me questions, and that is the purpose of this meeting. I've done justice to the one I know I can. Okay, so
I still don't.
Sorry,
Dr. Tony.
Sorry. Wait. Before you, I missed this slide. I don't know whether that's what you want to ask.
No, that's not what I want to ask.
Okay, wait. Just let me. Somebody was asking about standard deviation.
Yeah.
Okay, so you have the 68, 95, 99.7 rule. Okay, so for any study you do, okay, 68% of the results will lie within the first standard deviation. So now you do any study, let's say you are measuring the average birth weight for all the children born in England. Okay, so you are measuring the birth weight. So then you now plot it in a graph using computer. Okay, you went into the field and randomly selected 1,000 babies and measured their birth weight, and then you plot it on the computer. This is the graph you get. Remember, you used a randomizing software to generate numbers. Okay, so this is the normal distribution curve. This is what it looks like when you say normal distribution curve. This is what.
Yeah.
Now, this center, the apex here, is the mean. The mean. Okay, so this one is what the deviations from the mean. So between here and here is 68%. So 68% of the 68, 95, 99.7 rule. It says that what 68, even if that's research that you did, if another person do it, or if you did it well, if 100 persons do the same research, okay, or if that research is repeated 100 times, okay, 68% of the results will fall between the mean and the first standard deviation. While 95% of the results will fall between the mean and the second standard deviation. All right, then 99.7% of the results will fall between the mean and the third standard deviation. Okay, so that means if you repeat that studies over and over again, this is the distribution. So anything that falls outside here is outlier. It's likely it is not from the same population. All right, so time for questions.
So I don't understand this one. This is not what I want to ask, but
ask.
68% of the results will fall between the mean and the first standard deviation.
Yes, this is the mean.
How do you calculate standard deviation, please?
Standard deviation. Okay, let's ask Google. You don't need to. You don't need to know the formula. So let's ask Google. Okay, so formula for standard deviation. You know, sometimes we focus on the formulas, but we don't know how to interpret it. So this is the formula for standard deviation. Let me see. Okay. Let me open this one. So how to calculate standard deviation? Okay. Can you see my screen?
No,
I cannot see the standard deviation side.
Okay. Let me stop sharing again, and then share. Okay. Okay. Can you see my browser now?
Yeah.
Okay.
Okay. So you just use Google. Google will tell you the formula. So you can see here. This is the X is the mean.
Okay.
Wait, just calm down, though. Just small, please.
That's why that's what I'm saying. Like it's not a mathematical.
I don't need to cram this thing, Abby.
You don't need it. That's what I'm saying. Like
I don't need it.
Okay. It's not like in Nigeria where they are always emphasizing on after cramming it and you don't know how to use it, interpret it in the research paper. How will you do it? So basically, for each this X is the mean, the average. So let's say you collected 1,000 a birth weight of 1,000 babies, and then you find the average. The average is X here. Okay. Now this mu is each of the data sets, each of that 1,000 birth weight, each of them. You get the mean, then you minus the value. So mean minus sample number 1, birth weight number 1.
Okay.
Then like that, 1,000 times. So mean minus sample number 1. You write it. You put it somewhere. Mean minus sample number 2. You write that somewhere. So after you have done that thing for the 1,000 of them, okay, the result that you got, you will now square it. Okay.
Square each of them.
Yes, each of them. So that's a long calculation now. So you now square each of them for that 1,000 birth weights. Okay. After squaring it, this thing it means sum. So you now add it up. Okay. For that 1,000 birth weight. Then after adding it up, you now divide it by 1,000 because 1,000 is the total number of the sample size.
Okay.
And after dividing it, you now find the square root. Okay. So when you find the square root, that square root you have gotten is the standard deviation.
Standard deviation for the entire data.
Yes. No, the standard deviation for the mean. So
for the mean.
This is the mean now. Okay.
Yeah, on that graph, you are saying first standard deviation, second standard deviation. I mean, so how did we get?
No, what I'm saying is this one now is we are assuming 95% confidence interval. Okay. We are assuming that which is the one that we normally use. So the 95% confidence interval is based on the second standard deviation. You get that?
I don't know what confidence interval is.
Confidence interval means that if you repeat a research 100 times, if you repeat a research 100 times, that the value you will get, the result of that research will lie within that range of the confidence interval. That's the meaning of confidence interval.
Oh.
Sorry, I didn't get that.
So if you repeat a research 100 times, 95% of the result that you get will lie within that confidence interval.
Okay.
And for you to calculate confidence interval, you can use software to do that, and then there are formulas that you can also use to do that. Okay. So the issue of standard deviation is all about the difference between the mean. Is just trying to explain the variability, how that 1,000 babies, how their weight varies from the mean. That's the purpose of standard deviation, to explain the variance between the mean and the entire data set. Okay. So, any questions based on other things or any clarification? Based on
I still don't know how. I mean, I still don't know this last graph now.
Which one?
I still don't get
this
the.
This one. Are you seeing my screen?
No.
Oh, what are you saying?
Standard deviation.
Okay. What's the question?
The last graph, where we had the 68, 95, 99.7 rule.
Okay, wait. Let me share that one. Wait. I think I'm in another place. Okay, so you mean this one?
I still don't get it. What am I doing with it? I mean,
I'm saying that it's just for your understanding. They're not going to ask you to calculate it. It's just for you to understand how it works. Okay.
What am I understanding, please?
Yeah.
That's the 68% of results.
Explain this.
Wait, 68% of the results will fall between mean and the first standard deviation.
Yes.
What will I use that information and do? I mean, you
it's
understand
just a rule. It's just a rule that if you do your research very well, there's any research that you're doing, if you do it very well, and then that research is repeated 100 times, about 68 times of it, the result will fall within this mean, the first standard deviation. Okay.
So does it have any connection with the confidence interval? Because you said almost the same thing about confidence interval.
No. For confidence, for mean, in mean, you are looking at the sample. You are looking at a point estimate. Hello, can you mute your mic? Who is making noise?
Okay.
So now in mean, you are looking at a point estimate. A point estimate. That means like you are looking at average weight of a particular thing. That is mean. Okay. But when you talk about confidence interval is a range. Is a range of values whereby the results, whether it doesn't matter the result, whether it is odds ratio or whether it's relative risk or whether it is mean difference, the results of the study are going to fall within that confidence interval. So let me get a graph of confidence interval so that let's look at it. So confidence, can you see my screen?
Yeah.
I mean, what are you seeing?
We're actually seeing the normal distribution graph.
No. I've left that one. Okay, so so they're saying this is, I'm just using Google. So this is confidence interval that you are asking me. Okay, let me open this one. Okay, so you can see it's defined as, we said what, that we are assuming normally in research, we normally assume 95% confidence interval. That's the one we are using. Okay, so let me open. Oh, sorry. Let me open this one. Open image. So where's the image now? So can you see this one now?
Yeah.
Yes.
So the 95% chance so that your population mean will fall within this area, within these two areas. The 95% chance that your population mean will fall within this area. So now these two areas, like I said, just like the mean, or the one for the mean that we said. So those two areas are within the 95% confidence interval. Can you see the graph I'm showing?
Yes.
Yes.
Wait, let me see. Okay. So now, if you repeat an experiment 100 times, okay, 95% or 95%, sorry, 95 times, the results of that experiment will fall within this area between the lower limits and the upper limits. So now, normally the upper limit is 2.5%. If you minus, remember it is 95%, right? So if you include this one here, 2.5 plus 2.5, that's 100%, right?
Yeah.
Okay. So now we have only 5% that is free. Remember that this is the normal distribution of the curve. This is the normal distribution curve for a randomly selected sample. So inside a normal distribution curve, if you remove 2.5% from the upper limit on the upper limit and remove 2.5% from the lower limit, you have the remaining 95%. So any result that you are getting from your research will fall within this 95%. Okay. So when you say that something is not significant, is when it falls either on this side or when it falls either on this side. Okay. So that is why your p-value, if you remember when we said that what the p-value is less than 0.05, is that this is what we are talking about.
Okay.
That means the chance of the results falling within the chance of the results falling outside this range is less than 5%. So this is where we get that 5% that we're talking about, that we always talk about. So this is just an assumption in research. Okay, that on a normal day, if you do your research very well for a normally distributed data, most of your results will fall within this boundary. And this boundary is also, so that person that asked that question this is similar to the thing that I shared before on the screen. You see the same principle because it's the normal distribution curve. Do you get me?
Yes.
So it means that you are right. You are right. It's still the same because it's the same normal distribution curve. Can you see can you see my distance?
No.
That's 68, 95, 97.
No.
Can you see it? Okay.
No.
Not yet.
I don't know where now. Okay. I need to share it again. So it's the same principle because normal distribution is the same everywhere. It's not about whether you're dealing with mean or whether you are dealing with the normal sample. You see the same principle. So it is from here. Hello? Hello?
Yeah.
Yeah.
So the person that asked the question, can you explain to me what you understand? They are the same. Can you explain to me what you understand?
You said something like when you carry out the experiment or study plenty times, that the result you get you
I'm just
fall
using 100.
within.
Remember, I said 100 because it's 100%. Okay. So assuming you repeat that experiment 100 times. Okay.
Oh.
The 95% of the values. Remember, in the other graph that in the other picture, we saw that here is 5%. That is from here.
2.5.
While here is 2.5%. So the remaining 95%. Okay. So if you watch 2 sigma, that means what? 2 standard deviation. 95%. So here and up to here, that's 95%. So anything here is now outlier. Okay. So if the result of the study falls inside this area, it means that the result is not significant. Is that clear?
Okay.
No.
So am I supposed to have this graph?
No, now I'm just trying to explain.
No, wait, let me land now.
Okay.
Before I start carrying out the experiment also, am I supposed to have something like this?
No, you are not supposed to. You are not. This is an assumption in research. You are not supposed. I'm just trying to explain it. Nobody will ask you to draw the graph. I'm just telling you the only thing that you need for exam is that when your p-value is less than 5%, the result is significant. When it's above 5%, the result is insignificant. That is all you need. If you are doing a research, you're not going to be drawing all these things. This is just to understand where we derived all those things we used to say that when the p-value. So what is p-value? What is p-value?
Probability.
It says the amount of variation in the results that are due to chance. That's what I'm not sure if I understood that anyway, but
good. That is correct. Good. That is correct. So if your research, if out of 100% of your research, only 1% can be explained as due to chance. What is the p-value?
Getting more confused though.
So that's 0.01.
Correct. As simple as that. I mean, if you are doing a research now and only 1% of the result can be due to chance, it means that your p-value is just 0.01, and that means what? That your research is what?
Homogeneous.
Very, very, okay. Yeah, using homogeneous.
Yeah.
Homogeneous is for when you're combining studies.
Meta-analysis.
That's for meta-analysis. So don't confuse them. But it's still the same principle, all right? It's still the same principle. It just shows you that you did well in your research. The results are significant. All right.
Yeah.
So I hope that clears the confusion. So they are
similar.
Okay, Stella. Oh yeah. What is the problem again?
I was actually following you, but along the line,
ask question now. I don't know. I cannot repeat what I said.
From where I actually got lost is from that graph where you're asking when you say something about the 0.05 that is P for p-value. I understood that of 95%, but that remaining.
Okay, so can someone explain to her what p-value is, please? We have spent beyond 1 hour, so I'll be expecting extra. Someone should explain to her.
Please put the graph on so that I'll be seeing the.
Is it this one?
No, I'm just seeing only your picture.
Oh, can you imagine? I didn't know. Sorry, I thought I was sharing my screen. Okay. So this is the last question. No, we are done for today.
No, I've not asked that the question. That's not the last question.
Calm down now. Wait, let me get my own clear, please. Okay. From this graph now, at least I was able to get when you said about the 95% of your study will fall within so value, but the other ones I didn't get it. Like,
what is it that you didn't get?
2.5% that is on the both side that is remaining.
So can someone explain to her now, beg?
Benedict.
So you already said it. You said it already in terms of the you said 5. You said that p-value is the probability of your research not happening by chance. Yes.
Okay.
No. P-value is the probability of your research being due to chance. Okay.
Due to chance.
Okay.
Yeah.
Okay.
Yeah. So that means that if your research is significant, it has to have a low p-value. Okay.
Okay.
So it shouldn't be due to chance. Like that means all your effort is just a waste. So
sorry, I want to ask.
Stella, that's the most important thing you need to understand.
Yeah. Okay, I want to ask now. In our research that we're going to write next semester, does this apply there too?
No, because you are not writing a quantitative. You're not doing quantitative research. You are doing qualitative, right?
Okay.
Or you're doing a systematic review, so it doesn't apply. Is after you have gotten your MPH, if you now want to do quantitative research, all these things will become like hospital then.
Okay.
It's just for epidemiology and statistics. Okay.
All right.
Next question. Okay, can we call it a day? So
that
now. So I'm assuming that we understood at least to an extent. So I want to be getting questions in the group. If I'm not getting, it's telling me that you people are not reading, no? Because there's not how you can understand. Do you know how many years it took me to come to before I can understand? Like compress something in 2 hours.
Yeah.
So you cannot tell me that you understood that the whole 2 hours. So that's why I'm here. So ask in the group. I will respond using an audio message or using a picture. Okay.
All right.
So and then I think I've given you guys guidance on some the other subjects. So I wish you guys good luck. So
thank you so much.
Try and invite your friends. Okay.
Thank you very much.
Any question? No. Any question? No.
Is in the forest.
That you wanted to ask
now.
your question. I think did you ask your question?
Okay,
I did not ask.
What's the question?
You in that forest plot, you did not show that diamond or something. That's that.
Okay.
Four-sided.
So you want
odds ratio.
Yeah.
Okay.
It's not always be diamond now. It might show up in another way.
Like, can I be asked to interpret an epidemiological study
you want diamond,
in exam, Dr. Tony? Hello, Dr. Tony, are you there?
I think you went to look for that slide.
You went to look for what again?
As in that slide that shows the diamond. It must not show diamond. You should just understand that the last thing there will be like the pooled results. So if the pooled result is touching one.
Yeah, just refer to the video that I've already done before. Okay,
it's from the video now that I got this question. I don't understand it.
Okay, you don't understand the big diamond thing there.
Yeah.
Okay, what it means, is that what you're saying?
Yes.
Okay, now let's open this one. Can you see this one? For example.
No, we are not seeing anything.
My screen. Okay. Oh, I'm not sharing my screen. Okay. Where's Zoom? Okay. Where's Zoom now? Okay. Share screen. Where's the browser? Okay. All right. Good. So can you see the big diamond that you're asking me?
Okay.
So you want to see it? So you have seen it now. Are you happy? Okay. Good. So this is what? Is it forest plot or is it funnel plot? Which one is it?
Forest plot.
Forest.
Plot. So you see it in meta-analysis, right?
Okay.
So, good. So now you might see something like this, and they're not asking to interpret.
Yeah.
The next thing is to interpret is not about trying to find formulas. Interpret what you have done, because most times it's computer that will generate all the answers. You don't need so much. So these are different studies that have been combined. So first question I want to ask, is this study significant or not?
Which one?
Not significant.
There are a lot of studies now.
First of all, what type of study is this? Is it what type of study is this? Is it a primary research or a secondary research?
Secondary research.
So what type of secondary research is it? Systematic review. Yes, and this is a meta-analysis. Okay.
Meta-analysis.
Yeah. Okay.
Okay, good. So the person that is asking me, so that's why you have different studies. So they're combining the studies together to get something, right?
Okay.
Now the first question I'm asking you now, as your examiner, is what is the exposure group? What are the two groups being compared?
Non-smokers.
Non-smokers.
All right, that's the first question. Second question, what is the exposure in this study? Smoking, right?
Yeah.
Smoking.
Now,
Smoking.
Third question, what is the outcome?
Development of
atrial fibrillation.
Good. Are you seeing it? Small, we're moving.
Yeah.
Now, next question. What is the effect size that is used in this study?
Oh, that's odds ratio.
Correct. You guys are doing well. Please, after today, if you people don't refer those your students, they are very ungrateful. after teaching them for first semester.
Mind them, that's what they should do.
All right. Okay, so let's continue. Okay, good. Now, what is we have identified the odds ratio. Good. Now, so I want to ask you another question. Hello, baby, stop talking. Let me.
Sorry.
Okay. So now for the first study, this one, McCleary et al. Is it significant or not? Sorry, not significant now. Is it what is is there an effect or is there no? Sorry, is there an association?
Association, yeah, not, yeah.
That is it?
Yeah.
Is there
no association?
Is negative association?
No, not negative association. There is no association. There
no
is
association.
no association between smoking and the
non-smoker.
Fibrillation.
Okay. Now the second study. This one.
How is there no association?
It's greater than 1 point.
Okay, sorry. I made a mistake.
What are you talking about?
Sorry. There is an association. You see, it's above 1. Okay, so there is an association.
It's positive association.
Yes, positive association. Okay, but now, apart from this one, what else can you see? Is it significant?
No,
not significant.
Why?
It crossed the line.
Okay, it touched the line of 1, right?
Yeah.
Okay. What else again can you say about this confidence interval? You can see how big it is. It has a wide confidence interval.
Yeah, so there are lots of variation. I mean, the study is not precise. I mean,
it's not precise, correct?
Yeah,
so
it's not precise.
The key word for confidence interval is precision.
Precision.
Okay. So the larger the sample, the more precise.
More precise.
Yeah. So that's why you need to recruit large samples, to get a very good result. All right. Let's talk about the second one. So sorry, how do you interpret the odds ratio for this first study? 1.36. Can someone let me see who will get this one now? Let me see who will get this one. How is the odds ratio for this one?
To be like 36%. I mean.
Correct? Yeah, correct. That's the same.
Yeah, I know.
No,
I'm trying to put the
interpret it for me.
English.
All right. Go ahead. Try.
The odds of
Yes, correct. You got
of the smoking causing
the odds of outcome.
grades.
Start from outcome. The odds of
the odds of the outcome. Oh, great.
Which is what? Atrial fibrillation. Okay.
Yeah.
Okay. So can you put it in your own words? So the odds of developing atrial fibrillation is
36% more.
Is what?
36%.
36%.
Higher or lower?
Higher.
Among.
I don't understand though.
You see? So who can interpret it, please? Can you? Because this is what you will see in exam. I'm telling you, if you don't see it, you better learn how to interpret it. It's not how you not learn how to interpret this thing. Oh yeah, who can make attempt? Please. Interpret. Remember, we remember that in the exam they will not ask you to interpret all these studies.
Okay.
The main one we are looking at is the diamond shape. Remember, for exam, that is the overall result. You see this diamond. That's the one we're looking at. So, but I'm just trying to test you to see whether you can understand how to interpret individual studies. All right?
Yeah.
Okay. So who can interpret this one? First one. 1.36. What does it mean?
The odds of having atrial fibrillation is 86% higher
among the exposed group.
Among the exposed group,
right?
No, we just mentioned among smokers. Just go straight.
Okay, among smokers compared to non-smokers.
Correct. Okay. And then, however, continue. You have not finished. However, interpret this side.
However,
I'm going no more.
Confidence interval is wide.
Yeah.
55.
Yeah.
Hey, however, the confidence interval.
Yeah, no.
I mean, however,
something.
Yeah,
and
correct.
it's already cold.
However, the study is not precise.
I tell you, not
yes, the confidence interval crossed 1, and therefore it is not.
Okay. It's not precise.
Okay,
so
you
that's
read
the
both Bradford and Manchester.
Please, can you mute your mic? Please,
somebody mute your mic.
All right.
Yeah.
Okay. Can someone attempt this one? Iguchi et al. 2013. Can someone try and interpret this one? Let's see.
The odds ratio is less than 1. Oh boy, sorry.
Okay. Can someone else interpret this one? Let's see. Any attempts on this one? Iguchi et al. Let me see those I got understood what I thought. Interpret 0.91.
The odds ratio is less than 1.
Correct. So what does it mean?
It means the exposure is protected. I'll not use protect because it's not intervention.
Exactly. You cannot use for protect.
Yeah.
Okay. So,
yeah,
but
because
then
it's not an intervention.
So here you will say that there is a that the odds of developing atrial fibrillation decreases by 9%. Remember, 1 minus 0.9. Okay. So the odds of developing atrial fibrillation decreases by 9% among those that smoke compared to those that do not smoke. However, the confidence interval crossed 1. Okay. Therefore, the study is not significant. It's not significant. It's not significant. Okay. Okay. And also, yeah, it's not significant. It's not about the precision now. The main thing is that it's not 1 and it's not 2. Okay?
Yeah.
Now look at this one. Can someone interpret this one now? Pardo et al. 0.76.
The odds ratio is less than 1.
Just interpret it now. We know.
Okay.
The odds of developing what?
Atrial
fibrillation is 7%.
Non-smokers.
So all this English I used to speak. The odds of developing atrial fibrillation is what?
76%.
7%. Oh, yeah.
7% lower.
Wait, it's how many percent? Wait, 76%.
76%.
76.
This is how you just fall the exam. This is less than 1. How do you interpret when it's less than 1?
It's 1 minus that one now. It will
so
now
1
be
minus 0.
0.34.
0.24. So go ahead and interpret it. How will you interpret it?
The odds of
developing
atrial fibrillation is 24% lower.
24% lower, correct. In smokers, always use in smokers compared to non-smokers. Okay. Now look at this one. The confidence interval is what? Narrow.
It's narrow, yeah.
Okay. The
study is precise and significant.
Yes, it's significant. It's significant, correct. Good.
Okay. Sorry, please. How did you get 24%, please?
1 minus
0.76.
Because it is less than 1, no?
Yeah. Okay. I have to subtract 1 minus. Okay, when it's less than 1.
All right. Yeah. So now let's look at the one that you'll be asked in the exam.
Yes, so
the result of the meta-analysis. Oh yeah, interpret this one now. This one is the main one though. All these ones is just preamble. We're just trying to stretch your muscle. All right. So interpret the result. This is the one as if it's exam. This is what you just test it like this. Yeah. And give you the diamond shape. Who is the person that was asking me about diamond? I want to see diamond shape. Oh, yeah.
It's me now. I don't understand it. So
interpret it. So it's something you did here.
Okay.
Yeah.
The odds ratio. I mean, the pooled odds ratio now is
correct. Pooled odds ratio. That's the right.
The pooled odds ratio. I don't know. It touched the line now. Okay, it's 1. Pooled odds ratio is equal to 1.
Correct.
So there is no association between the cause and the effect.
Between smoking, wow, is that how you say it? Between smoking
and atrial
fibrillation. Okay. So now, then it crossed the line, right?
Yeah.
Okay, so
making the studies not insignificant.
Correct. That means making it not significant. Now, look at this one. What does this one now stand for?
Yeah. P value is less than 0.00. I mean 0.05 now, right?
Yes. Calm down. What is this one? This I squared.
Higgins I squared. It shows the amount of variation.
So how will you interpret Higgins I squared of 73.1%?
That the variation between the studies are 73.1% high.
Okay. Now the p-value of the Higgins I square.
Yeah.
Okay, I feel that there should be a mistake in this study because on a normal day this p-value here is supposed to be the p-value for the odds ratio, right? So this odds ratio. Okay, wait.
Dr. Tony, yes, that is it. You want to see? There is something I noticed when I watched the video. You said that when p-value is less than 0.05, the studies are heterogeneous.
No, you are mixing it. Are you sure?
Okay, for meta-analysis. I mean, that's what I wrote in my jotter, unless I heard wrong.
Okay.
Yes, that's what I had to now cancel it now and rewrite homogeneous.
No. That means I made a mistake. Let's see.
Oh my God.
Let's see. Chi-square test, because these things you got to be doing it.
No, where did you see it from? You
In
said
the video now, when it's less than 0.05.
You guys are not confusing me.
If it's less than 0.05, it means that there is heterogeneity, but it is low heterogeneity. That's what it means.
What are you talking again?
Are you sure?
But that was exactly what was in the video.
Yeah, 0.5.
You guys should not confuse me because chi-square test of heterogeneity. Okay. Okay, now the test assumes that the can you see my screen?
Yes.
Now, the test assumes that the null hypothesis of all the studies are homogeneous, right?
Okay.
That is the null hypothesis, and that each study has an identical effect. Okay. Now, if the p-value of the test is low, you see, you guys confused me. You see? So you are correct. If the p-value of the chi-square test of heterogeneity, we reject the hypothesis, and we will say that heterogeneity is present.
You want to confuse me, all of you.
Can you see that?
I know what I was saying. Dr. Tony, you agreed with them. I had to cancel what I wrote in my document to write homogeneity.
Oh, sorry for that. Sorry for that. So when because look at what the null hypothesis is saying. On a normal day, the test is already telling you that the studies are homogeneous, right? So if the p-value now becomes significant, we reject null. So hello. So can you make sure you are writing the correct thing? If the p-value of the chi-square test of heterogeneity is low, it means there is what? Heterogeneity. That is what it means. Okay? Not homogeneity. Is that clear?
Yeah.
All right. So now, if there is heterogeneity in the study, what model do we use? Are we going to use fixed or random effect?
Random.
Good. So, and remember the various categories of heterogeneity. So you can see that study had a high level of heterogeneity, right?
Yes.
Can you see? Yes. So everything is now making sense. So as high as 73%. So these studies are not similar at all.
Yeah.
All right. Thank you so much. We're going to stop here. I enjoyed my time with you people. Please
thank you.
Thank you very much.
Yeah, thank you.
Okay. All right.
Thank you very much.
Universities and teaching people. Thank you so much. Bye-bye.
Thank you.
Bye-bye.
Right.
Bye.
Bye. Ada,
I love.
WhatsApp, please. I beg you, the name of the Lord. Come on, WhatsApp.
Okay. No matter.
Okay. Bye-bye. I want to stop the recording now. Bye.
All right.